Your feed generator containers are OOM-Killed every 10 minutes. CPU is fine, but memory is the killer. You assume a memory leak, but the real culprit is loading full user profile images for every video in the candidate pool. Let me show you exactly why that happens and how to fix it. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design TikTok. TikTok's feed is a personalized, infinite scroll of short videos. Unlike a simple chronological feed, it uses a hybrid approach: pre-compute feeds for active users and compute on read for inactive ones. This balances latency and write amplification. The core problem: querying all videos for every request is too slow. The solution is a two-tier approach. For active users, when a creator uploads, we push the video to followers' caches, fan out on write. For inactive users, we compute the feed on demand, fan out on read. This saves storage and write amplification. Here's the feed generator code. It checks cache first, then computes on read if needed. On new video upload, it evicts the cache for active followers so they get the new content on next request. This is the fan out on write pattern. Video storage is the biggest cost. Raw videos are transcoded into multiple resolutions and stored in object storage. To reduce content delivery network egress costs, we use a two-tier content delivery network. Edge caches only the top 1% viral videos, regional caches top 10%, and the rest come from origin. This cuts costs by 60%. This code implements tiered caching. It checks edge, then regional, then origin. Only viral videos are promoted to edge cache. This ensures hot content is served fast while cold content doesn't waste edge space. The recommendation system is the secret sauce. It uses a multi-stage pipeline. First, retrieve candidates from follows, trending, similar users, and content-based sources. Then rank them with a deep learning model. Finally, apply diversity and freshness filters. The funnel ensures speed and accuracy. Here's the recommendation pipeline code. It retrieves 500 candidates from 4 sources, ranks them, and filters. The retrieval is fast using ANN for content-based search. The ranking model is a lightweight neural network. A single viral video can cause a 10x traffic spike. The system must handle overload. Use queues for video transcoding, content delivery network for caching, and circuit breakers to fall back to stale feeds when the feed generator is overwhelmed. This circuit breaker pattern prevents cascading failures. If the feed generator times out 10 times in a minute, it opens the circuit and returns stale cached feeds. After 30 seconds, it resets. This keeps the system responsive during spikes. This is the same issue we highlighted at the start. Here's exactly why that happened. The feed generator was loading full video metadata including user profile pictures for each video in the candidate pool. For a pool of 500 videos, that's 500 user objects with profile images. Each image was 500 KB on average, leading to 250 MB per request. With 20 concurrent requests, that's 5 GB over the 4 GB container limit. The fix was to lazy load user profile images only when rendering the feed card. This reduced per request memory from 250 MB to 2 MB. Also added a per container request concurrency limit of 10. The key change was lazy load profile images. This is the exact line that caused the OOM incident. Loading full user objects including profile images for each video in the candidate pool. Only load what's needed for ranking, then hydrate display data later. If you fan out to every follower, a celebrity with 10 million followers causes 10 million cache updates per video. That's huge write amplification. Mitigation: only fan out to active followers, those logged in within the last 24 hours. Caching every video at the edge is expensive. Only viral videos should be cached at edge. Use a view count threshold to decide. Otherwise, you'll see content delivery network costs skyrocket. New users have no interaction history. The retrieval returns nothing useful. Solution: use a default model based on device type, location, and time of day. Force show a few popular videos to bootstrap the profile. Never transcode videos synchronously on upload. A 4K video can take minutes. Use an async queue and return a processing status. The client polls until ready. The article uses Java-like pseudocode but does not specify a runtime. In production, the feed generation service often runs on the JVM, e.g., Java 11+. Ensure that duration of minutes and atomic integer are available, Java 8+. For Kotlin users, the syntax differs slightly, e.g., atomic integer 0 versus atomic integer 0. No breaking changes in recent versions, but be mindful of GC tuning for low latency feeds. The article mentions prepending to a pre-computed list, but does not show code. Here is a concrete implementation using a readies list to prepend the new video to each active follower's feed, capped at 500 entries. The article mentions new users, but does not explain the cold start problem in depth. When a user first joins, there is no interaction history. TikTok uses a default model based on device type, location, and time of day, and shows a few popular videos to bootstrap the profile. This is critical for retention because a poor first feed can cause immediate churn. The article discusses tiered caching, but omits cache invalidation. When a video is removed, e.g., copyright strike, you must invalidate it from all content delivery network tiers. Use a purge API, e.g., CloudFront create invalidation, but be aware of rate limits. For urgent removals, consider a block list at the edge that is checked before serving. To debug OOM issues, take heap dumps and analyze them. Profile per request memory usage. Set container memory limits with a buffer. For circuit breakers, monitor failure counts and adjust thresholds. Let's run through some common interview questions. How does feed generation handle a user who follows 10,000 people? Uses fan-out on read, fetches recent videos from all followees using a time-ordered index. When to choose fan-out on write versus fan-out on read? Fan-out on write for high read-to-write ratio, low latency. Fan-out on read for many followers or storage concerns. How to prevent thundering herd on origin storage. Use request coalescing, readies mutex, and pre-warm content delivery network based on view count velocity. And a few frequently asked questions. How does TikTok generate feeds for 1B users? Hybrid, pre-compute for active users, compute on read for inactive. How does TikTok reduce content delivery network costs? Tiered caching, edge for viral, regional for popular, origin for rest. Content-aware compression. What happens when a video goes viral? Content delivery network absorbs most traffic. Request coalescing prevents thundering herd. Circuit breaker falls back to stale cache. To recap, TikTok's feed system uses a hybrid approach to balance latency and write amplification. Video storage uses tiered caching to reduce costs. The recommendation pipeline is a funnel for speed, and circuit breakers plus lazy loading keep the system resilient. Ready to go deeper? Up next, design Reddit, then design Tinder, then design Spotify. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.